Hello everyone, today we are going to dive into a fundamental concept in signal processing, finding the Fourier transform of the sine function. As you can see on the screen, we have a classic sine wave, which is the function we'll be analyzing. Alright, let's start by defining our problem. Our goal is to find the Fourier transform of the function f of t equals sine of omega naught t. If you look at the figure on the slide, you can see a graph representing our function f of t. The horizontal axis is time t and the vertical axis shows the function's value. The function itself is this beautiful continuous blue sine wave. It oscillates smoothly and periodically around the horizontal axis, starting at the origin and extending infinitely in both directions. Now the continuous Fourier transform, which we denote as f of omega, is defined as the integral from negative infinity to infinity of our function, f of t multiplied by e to the power of negative iota, omega t dt. The most direct way to tackle this is by using a very powerful tool, Euler's formula. So for our second step, let's express our sine function using Euler's formula. As a quick reminder, Euler's formula tells us that e to the power of iota theta equals cosine of theta plus iota times sine of theta. From this fundamental identity, we can derive an expression specifically for the sine function. It turns out that sine of theta is equal to e to the power iota theta minus e to the power negative iota theta, all divided by 2 iota. Now we can apply this directly to our function. By replacing theta with omega naught t, we get that sine of omega naught t is equal to e to the power iota omega naught t minus e to the power negative iota omega naught t, all divided by 2 iota. Next up in step 3, we are going to take advantage of a really helpful property of the Fourier transform, its linearity. What this means is that if you have a sum of functions, you can just take the Fourier transform of each part separately and then add them up. You can see the formal definition on the slide. So, applying this to our expression for sine, the Fourier transform of sine of omega naught t becomes the Fourier transform of that entire fraction we just derived. Because 1 over 2 iota is just a constant, we can pull it out front. This leaves us with 1 over 2 iota multiplied by the Fourier transform of e to the power iota omega naught t minus the Fourier transform of e to the power negative iota omega naught t. Okay, for our fourth step, we need to know the Fourier transform of a complex exponential. This is a standard result that you'll use all the time, and it involves the Dirac delta function, which we write as delta of omega. The rule is that the Fourier transform of e to the power of iota at is simply 2 pi times the delta function of omega minus a. What this represents is a single sharp impulse in the frequency domain located right at the frequency omega equals a. Now we can apply this to the two terms we have. For the first term, our AR is omega naught. So its Fourier transform is 2 pi times delta of omega minus omega naught. For the second term, AR is negative omega naught. So its transform is 2 pi times delta of omega minus negative omega naught, which simplifies to 2 pi times delta of omega plus omega naught. In our final step, we substitute these results back into our earlier expression. After simplifying by cancelling the factor of 2 and replacing 1 over iota with negative I, we arrive at our final answer. This result is shown in the plot. Since the answer is purely imaginary, we see two impulses. There is a positive impulse of pi at the frequency negative omega naught and a negative impulse of negative pi at positive omega naught. This visual perfectly represents our final simplified expression. And here's our final result. The Fourier transform of a sine wave is a pair of imaginary impulses in the frequency domain. The equation shows these are delta functions located at positive and negative omega naught. As the plot illustrates, this gives us two sharp symmetrical spikes. One impulse is at the positive frequency, omega naught, and the other is at the negative frequency. This beautifully shows how a pure sine wave is composed of just two distinct frequency components.